This is video number 9 for Computer Science 3344. We are talking about Turing machines. We've only looked at a couple, but they're pretty involved, so even just talking about a couple takes a while. This one is going to be different. This is going to be, I'm going to drop down a little bit. I'm going to call this a calculation-based, C-A-L-C-U-L-A-T-I-O-N, calculation-based Turing machine. Now, there's actually a famous result in theoretical computer science, mathematics that's related to computer science, called the Church-Turing thesis. I wasn't intending to write that on the board, but now that I've said it, I will. C-H-U-R-C-H-Turing thesis. They both more or less simultaneously, but from different perspectives, came up with the same result. And what it has to do with us is, one interpretation of it is that anything that any computer can do whatsoever can be represented as a Turing machine. And that just seems ridiculous. That's about as ridiculous as your favorite DVD, your Frozen 2 DVD, being nothing but zeros and ones. Shiny places and dull places burned in a little piece of metal sandwiched in plastic. It's unbelievable! It's also unbelievable that anything a computer can do can be done with a Turing machine. Because we already know what a Turing machine is. It's just got those zeros and ones typically, and one tape that we can go back and forth on, and then sort of a control unit that changes state. And that's it. That's all we have to work with. So that's why I even bothered to write the Turing thesis up here, named for Alonzo Church and Alan Turing, because it's just such a surprising result. After you're used to modern computers that we have today, the calculation-based Turing machine, it is kind of new ground for us, because I think just about every machine, if not absolutely every machine we've looked at this semester, all it can do is recognize languages. All it can do is say yes or no, that string is in the language, or it isn't. And the one I want us to look at now, going a little bit further, let's do binary addition. And if I had it to do over again, I wouldn't call it binary addition, I would just call it addition. Because of course, everything at the lowest level in the computer is done in binary. So this is redundant. It's got to be broken down into zeros and ones, and you already know how numbers are represented as zeros and ones, so that's no big deal. So let's start just by looking at a couple of examples, just to refresh our memories how binary addition is conducted in the first place. Let's see if we can handle this. Example 1, I'm going to add 1, 1, 1 as the first operand to 1, 0, 1. And I'm saying that slowly and deliberately because we are going to have to be very careful watching our own procedure for doing this addition. Otherwise, we're not going to be able to teach a Turing machine how to do it. Now, weird thing after another. Here's one weird thing. I'm going to draw a little arrow from nowhere coming in with a 0 on it. Why? Because all except the first column are going to have a carry in from the previous column of either 0 or 1 after the addition's done. And that way I kind of finesse away the special case of, oh, well, I've got to treat the first column differently. I don't if I go ahead and pretend like I have, that's a 0 by the way, if I have a carry in from nowhere of 0, then I can treat that column just like all the others. Now, here we go. 0 plus 1, that's 2, but a 2 looks like 1, 0. So I put a 0 down for the sum bit and carry a 1 to the next column. Ah, yes, it all comes back to you. 1 plus 1 is 2, plus 0 more is still 2. I put a 0, carry a 1 to the next column. 1 plus 1 is 3. But a 3 in binary is a 1 in 2's place and a 1 in 1's place, so it looks like an 11. So I'll put a 1 and carry a 1 to the next column. The next column is non-existent. If I carry 1 off the edge, I can just copy that down without adding anything. And without even knowing what those numbers are in base 10, we could figure it out, but we don't really care. There you go. There's a binary addition problem. That was short and sweet, kind of, sort of. I've got room for example 2, so I'll slip example 2 over here. Example 2, let me add 1, 1, 0 and 1, 0, 1. I'm not quite sure what additional this is going to illustrate. I suppose in my grand master plan, when I first looked at it, I thought this might bring up some cases that the first one didn't. But let's just go at it and see what happens. We've got the 0 carried in from nowhere, so that every column has its own carry to have to worry about. 0 plus 1 is 1. I put a 1, carry a 0 to the next column. 0 plus 1 plus 0 is 1. I put a 1, carry a 0 to the next column. 0 plus 1 is 2. I put a 0, carry a 1 to the next column. And once again, there's nothing over there in the next column, so I can just bring that 1 down and be done with it. And there's the sum of those two binary numbers. Now, I do need some board space. This is going to be real tough, not to completely fill up the board and then have to erase everything. But example 1, we've already gotten all the mileage out of that one we need. So I'm going to leave example 2 and sort of annotate that. I'm going to call this the first operand. Why will I call it that? Because that's what it is. It's the first operand. It's the first number that we're adding up. This is the second operand. This is the sum bit down here. In other words, that bit is part of the answer we're going to get. These are intermediate results. These are called carry. Now, you'll notice I didn't call it carry in. I didn't call it carry out. That's because in this loop that we'll be going through to actually perform this addition, it is initially a carry in, but then we have a carry out that becomes a carry into the next column. And labeling it both carry in and carry out, I'm afraid might be confusing. So I'm just going to say it's a carry bit that goes on to the next column of the calculation. And hope that that's not too confusing. Now then, now that we've got those two operands and names to call the different numbers that are involved, let's see if we can set up a Turing machine that will actually do that. Sounds simple, doesn't it? Let's take a look. I left space up here on purpose. I'm going to put the initial tape up here. Remember, a Turing machine has a tape, and another cool thing about Turing machines, since we're the ones that's designing it, we can specify the format of the input tape any way we want. The initial tape, come up with any symbols we want, use any symbols for burned up ones and zeros we want. So I'm going to have a tape that looks like a bunch of squares. And the first thing I'm going to put on the tape is the first operand. So you might well think, well then 110. But actually no, since I get to decide, it's my Turing machine, I can do what I want. I am going to put the first operand in the first 3 squares, but I'm going to turn it around backwards. I'm going to put the 0 first, put the 1 next, and then put the 1 in 4's place last. So this is backwards. This is 1's place, 2's place, 4's place. We're down here, this is 1's place, 2's place, 4's place. Why? Just to go rogue and be arbitrary and wild and crazy? No, because when you were watching and I did the addition, I started with the rightmost column. Even though we might look at this and read it left to right, we start with the rightmost column when we're doing the addition. So I put this here because that's the first bit I'm going to use. Now, I can't just copy in the next 3 squares, I can't just copy my second operand, just concatenate it on, because my Turing machine, man, that's going to be very difficult for it to figure out where the first operand ends and the second one begins. In this case, they're both 3 bits, but there's no reason to limit it to that. So there's got to be some way to distinguish between the first operand and the second operand on my input tape, enter a delimiter. We can use any symbol we want. I'm going to use #, hashtag. I saw it in an example one day and I liked it, so I'm going with it. That's just a separator symbol. And then I'll put the second operand, which as it turns out is the same backwards and forwards. So even though it looks like I copied it down verbatim, that's actually backwards. That one right there is that one, that 0's there, that one's right there. You get the idea. And I also need a delimiter here for future use, because I'm going to start putting the sum over here where I didn't leave any room whatsoever, I'm going to put the sum bits over here replacing this infinite, well, not replacing an infinite number, but replacing some of these blanks. So here's the plan. I'm going to add a column, so somehow or other I got to add that 0 and that 1 and put it in the first sum position, which will be the first blank. Then I'll add the next column, that 1 and that 0, and put that over the next blank and so forth. So my answer will be backwards as well, but that's no big deal. I'll just read the answer and reverse it when all the calculation is done. Now then, what I stated now is just not exactly quite correct, because when we get ready to add the second column, we're not necessarily just going to add 1 and 0. There could have been a carry in from the previous column. Actually, it's a carry out from the previous column becomes a carry in to the second column that I need to remember. Now, one of the weaknesses of the machines we've looked at, especially the NDFAs, bless their hearts, there's just a finite amount of stuff they can remember. Maybe that has something to do with finite state machine. The state itself, if you remember, is really good at parity stuff. Like, I've seen an even number of ones. I've seen an odd number of ones. I've seen an even number of zeros and so forth. What it can't do is remember arbitrarily long things. Enter the stack. We can push an arbitrarily long number of symbols onto the stack. And I could put an arbitrarily long number of symbols on the tape. But it's going to make this addition a lot easier if I build into the states of the machine some of that finite memory. And here's an example. It only takes finite memory as I'm getting ready to start the next column. It only takes small finite memory, 2 different states to remember, well, the carry in is a 0 into that column, or the carry in is a 1. And I'll just use 2 different states to represent that. So I've got 2 different starting points. One starting point for adding a column is the carry in was 0. Another state is the carry in is 1. All of this I know is abstract and without structure and everything. It's all just kind of laying the groundwork for this. So here's my initial tape. And once again, I'm going to have to completely erase the board to put the stuff up here I want. But that's where we're headed. I'm going to be trying to do that addition problem the way that we'll have to train our Turing machine to do it. Now that that's gone, we see a constraint that makes things look wild and crazy and hairy and complicated in Turing machines that we didn't do with that. This was sort of a 2-dimensional problem. We had rows and columns. Not here. We just got rows. So we just kind of have to visualize, I suppose. We have to visualize that, believe it or not, that 0 and that 1 are actually in the same column. Yeah, that's why these operations, the little delta mappings and so forth, can get pretty complicated. I can at least label this. This is the first I think I can label it. I can't if the marker's dried out. Okay, this is the first operand. This is the second operand. And this, someday, eventually, will hold the sum. And there's no reason to store the carries. I mean, the carries just kind of go into deciding which state we go to next, just so we can remember whether we need to carry a 0 or 1 over to the next column. And thank goodness we're working in binary, because those are the only possibilities we got to remember. The only possible thing to carry from one column to the next is 0 or 1. Base 10, it would be anything, through the roof, all the different base 10 digits. We won't even go there. I'm sorry I mentioned it even. Now then, I'm going to explode up, if I can find a different colored marker that actually writes, I'm going to explode up that example 2 that we looked at so I can draw stuff all over it. So I do a zoom in and make a giant 1 and another giant 1. I'll even make them look like giant ones. There. Thick giant 1, another thick giant 1, and a giant 0. And I want to add that to a tiny little plus sign, because a plus line, look, we know we're doing addition. There's no reason to try to represent a plus sign on our input tape, on our initial Turing machine tape. We're adding that to 1, 0, 1. And we'll see how this works out. Perhaps I should have practiced I didn't, but we'll try it out anyway. There. Should be able to see that. Whether you've seen anything else on the whiteboard before or not. And what we're going to do is pretend like we are Turing machines, and we can't see this as a two-dimensional problem. Well, let me finish this out so it looks a little more like the tape. 0, 1, 1 is the first operand, and then the pound sign separates it from the next operand. So we have to kind of visualize it this way. We're moving this way on the tape. 0, 1, 1, pound sign, and then go back, like those old-fashioned typewriters. You do the carriage return. And then it goes 1, 0, 1, and then another pound sign. I'll get rid of the plus sign. Put it way over here. It was in the way where it was. Why would I need the second one? Well, eventually I'm going to have zeros and ones over there, and the delimiters really are that. They're to separate the sets of zeros and ones that mean different things in the addition problem. So this delimiter is eventually going to separate the second operand, what's left of it, from all these blanks down here. And the blanks go on forever. But we want to try to replace the blanks with the proper sum digits from the addition problem. Now, we'll see how well this works. Where do we start? Well, we start at the very beginning. Surprise, surprise. I'm going to start right here. Is the same color? Let me switch colors again. I'll use one color for the arrow and another color for the description. Here. I'm going to start right there and say that is step 1. Step 1 is to start. Of course it is. Except I'm going to generically, because we're going to be using step 1 for each of the columns. So I'm going to describe that as start new column. S-T-A-R. It's hard to write on a wiggly whiteboard. Start new column. Comma. That's the ugliest start ever. S-T-A-R-T. That's better. Start new column, and I'm going to write remember on the board so much that I'm going to abbreviate it REM. Remembering carry. Remember, we got to carry in a 0 to the first column, so we don't make a special case out of it. Now, when this slides over, because we're starting another column and another column and another column, it's not always going to be remembering 0, so I'm not going to put remember carry 0. It's just remember whatever the carry is into that point. Okay. Now, I remember the carry, I see the 0, and I'm going to remember what I've seen as a partial sum so far. The partial sum is that carry that's coming in from nowhere plus the 0, and big deal. So far, I've got 0 plus 0, but still, I need to remember that. I need to remember that the sum in the column so far is 0 as I do this. Here's where things get crazy. I got to go this way and skip over these ones. And when I see the pound sign, then I know I'm about to see the next operand. So when I see this pound sign, I do the wraparound thing and come back over here, and boom, there we are. All of that was step 2, which I'm going to describe as skip over the rest of the first operand. Skip over rest of first operand. Skip over rest of first operand. How do I know I'm done skipping over the rest of first operand? I hit the pound sign. That's what it's there for. So I've already done this. You know what? I left something out. When I make my mental note that the sum so far is 0, I need to burn this baby here. I'm going to make that an X. So that in my tape is also going to be an X. I know I'm not going to remember to keep the tape updated. You'll just have to do that in your notes. Okay, so we've used up the 0. We don't want to use that again. And we'll also want to know, looking ahead, we'll also want to know when we're going back, reset all the way back to the beginning, that we've already used that so that next time we'll start the column addition at the 1. So here we go. Skip over the rest of the operand, and it brings us all the way down there, which, you guessed it, will be step 3. Use a different arrow. Now we pay attention to this. We didn't just locate it. Now we're going to use it. Step 3 is going to be to add whatever we find there to that partial sum that we're remembering. Add to partial sum. It's called a partial sum because it wasn't a complete sum. What was the partial sum? It was whatever the carry-in was with whatever we found as the first bit of the next column. Zip, 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 zip. Go over there and find the next bit in the same column. That's where we lose a lot not having a two-dimensional Turing machine. We've got to do all this linear going back and forth. So now we found this, and we add that to the partial sum, and what do we end up with? To get what I'll call the column sum. In other words, we now know the complete sum of all the bits involved in this one column addition. The 0 carry in that's invisible, the 0 we found there, plus the 1 that we find here. Okay? Now then, I also need to burn this up. I'm not going to use that anymore. I'll replace that with a y. So I'll know when I'm going backwards, well, that's looking too far ahead. It's going to be a good idea to replace that with a y. And we'll see if we can see if the reason for that emerges later on, perhaps. 3. Add that to get the column sum. Got that. What's 4? Well, 4, here we go again. We've got to zip past all the remaining bits of operand 2. Hit that pound sign. Now we know we've got over here to the sum position. And how am I going to do this? I guess I'll come back here. See, I really should have rehearsed that. All of that was step 4. What did we just do? Well, step 3, at the end of step 3, we knew what the sum of the column was, and now we're ready to deposit the low order bit. So if the sum is 0, it's just going to be a 0. If the sum is 2, it'll be a 1. The lower bit's a 0. We put that there and so forth. So 4 is where we're actually trying to find the next blank. Look for blank. Not loof. Look for blank. Replace blank. I'll just call it sum bit. With sum bit. Technically, it's the low order sum bit. It's the bit that's on the right of our 2-bit column addition result. But the low order bit is the sum bit. The high order bit is what we're going to have to carry back all the way back to the beginning. So that's where we are. Look for a blank. Write the sum bit there. And I've completely lost track of what we had. We had a 0 coming in, plus 0, that's still 0, plus 1. So our sum is a 1, and we'll replace that blank with an actual 1. That is the first result of our sum. Now, not only do we need to do that, when we zip back all the way back to the beginning to get the next bit of the second column, we're going to need to remember what the carry in was. In this case, since the total sum was just a 1, then we dump a 1 there, and then we're going to remember a 0 going back. So here we go, all the way back up here, starting here. Take the scenic tour. There. That's step 5. What's the description for step 5? Well, just what I did. Go all the way back. To start the next column. And where I've remembered to, I've written whether we need to remember the carry or not, and in fact here we do. That is so ugly. Go all the way back, that word is back, to start the next column. That word's even worse. Column. Remembering carry. Okay, so I dumped a 1. There was not a 1 to carry, but I still need to remember that there was a 0. So when I come all the way back over here, I'm going to start in with step 1 all over again. And the machine goes through all of its transitions just as it did before. What are those transitions? Well, let's see if we can review here. Back before I messed everything up, we started right here, the top of the first column, with a carry-in of 0. The carry-in is always going to be 0 for the very first column. I had 0 plus 0, I got a 0. Mental note, I got a 0. There's an X. That means I've used up that 0. I'm going to leave that behind as I start going all the way down the tape until I run into this pound sign here that says, okay, you're about to hit the second operand. Get the next bit of the second operand. The first bit of the second operand, this is reviewing the first time through, was a 1. So I need to add that to the partial sum of 0 I was remembering. I was I was remembering. And now I know the sum of the entire column because I've got the 0 carry in and the 0 that was at the top, the 1 on the bottom. The sum of that entire column is just a 1 with a carry out of 0. So now I've got to remember that by which state I'm in, doing this zipper thing again, going all the way past the next pound sign. As soon as I cross the pound sign, then I'm going to be over here in either some digits or blanks, and I want to replace the next blank with whatever I'm remembering as the sum bit. Let me see if I can do the second column real fast. And I'll probably regret that. No, those are danger words there, real fast. But here we are again, the carry in is 0. So we're going to be in the same state we were over here. The only other possibility is that the carry in was 1. So we only got 2 states here for step 1 that we need. Either Q0 is carry in of 0, or Q1 is start over the next column, carry in of 1. Since here, the state that I'm in is going to be Q0, then I've got a 0, and I'll add that to a 1. Make a mental note, the partial sum of this column, it's not the whole sum, the partial sum of this column is 0 plus 1, also known as 1. I burn this in my wake, going behind, and I can even set it to X. I mean, once I've used it, I don't need to remember whether it used to be a 0 or it used to be a 1. All I need to do is remember that it's been used up and I don't need it anymore. So, I don't remember what we got. Yeah, I do. We've got a partial sum of 1. I've burned that 1 and left it behind me, and here I go. As soon as I hit this pound sign, I know I'm no longer skipping over 1s and 0s that are part of the first operand. I know I need to start looking for the next bit in the second operand, and I skip over the y's because those have already been used up. So I'll hit this 0 right here. When I hit this 0, I'm going to add the partial sum of that column, 1 plus 0, that's a 1. So the sum of this entire column is a 1. I'll leave this and put a y there. We still haven't discussed x's versus y's, have we? But in the second operand, I'll leave a y behind, and I'm making a dash for the finish line, rounding the pound sign. Now I'm over here into blank land, and I skip over the 1. There will be a 1 there. I skip over this 1 to get to the next blank, and then I replace that with a 1. And wait, there's more. Now I'm ready for step 5 to go all the way back and start the next column with the carry in of 0. I think that's why we need to distinguish between x's and y's. Yes. Our step 5, I kind of took a shortcut here. I need to actually go back across the bits that I followed on the way down here, but that would really mess up my board. But as I'm going backwards through all this stuff, I need to distinguish between x's and y's, because when I get back to an x, that's when I know I need to stop and turn around to get the first bit of the next column. If I put x's here, I would stop before I got all the way back to the beginning of the next column. You see that would be the case? That's why we need some sort of difference symbol for the burned out bits in our second operand than we needed in the first operand. The first operand, not only does that X represent a burned out bit, it's a stopping place when I'm trying to get back to the beginning of the input that I have not yet used. What could be simpler? You know what? Probably a lot of things. We still have a ways to go on this. I am not going to try to do the whole thing. I am desperately going to have to find a way to get some stuff on the board without cramming it so full of this tangled mess. But that's my problem, and I'll need to work that out in the next few minutes, because I'm going to stop this video right here, hoping that this was an intuitive walkthrough enough that you got your mind around what we're going to have to do. The next step, if you're looking forward to the next video, the next step is going to be, okay, for each one of these numbered steps, 1, 2, 3, 4, 5, how many different states of our Turing machine do we need? One of those, I think I've already made a case for it. Unfortunately, I'm afraid it's going to be the very simplest one. Step 1 right here, we only need 2 possible states. There are only 2 possible carry-ins when we're starting a new column. The ones where we're going to have to be careful with state glut and more states coming up per step are when there are several different possibilities, not just a 1 or a 2. And you've had hints of that. For example, there's different possibilities of this column sum we could have down here. It could be 00, it could be 01, it could be 10, it could be 11. We've got to cover all those cases separately. Oh no. Well, we don't have to do it now, because I'm going to abandon this and I'll see you online.